Hello world, Servus Linz, and welcome to Pattern-Based C#. Today, Stefan and I are going to take you on a whirlwind tour of C# language patterns.
Patterns. Do you mean that we can, at runtime, check our instances against a certain shape, and then, well, if it succeeds, for example, print text to the console?
Yeah, not quite. Like, pattern matching is a really, really cool subject, but it's actually not the one we're covering today, because pattern matching is about checking an expression for specific characteristics, whereas we're going to be talking about compiler-recognized patterns. So language features that don't rely on interfaces or inheritance, but rather on a type's shape.
Shape. So you mean something like we could have a dynamic instance and then just for each it as if it was enumerable?
Kind of, but dynamic does allow you to bypass type checks at compile time, whereas we're going to be talking about type-safe patterns of the C# compiler. So yes, we will make our very own type for eachable in this talk, but we'll do it in a compile time checked fashion.
I see, because, well, with dynamic, if we have actually at runtime an array that is quite for eachable, but what if we have an integer? Well, this one is not for eachable. Compiler compiles it happily, but at runtime, how to enumerate A1. So are you saying that we could, for each our talk instance or talk type instance, even without it implementing the IEnumerable interface?
Yes, we can, and we will in just a little bit of time. But before we get into all of the coding, well, first of all, I do want to say that we're going to do a lot of live coding in this talk. So if you're in the back, I just want to mention that there are quite a few seats up in the front. It might be easy on the eyes there. And we also have a little something to keep things fun and interactive, namely a quiz. Woo! So everybody take out your phones right now, scan this QR code for the chance to win some really, really awesome prizes. And if you don't know the answers straight away, don't worry, everything is directly based on what we'll show you today. So just follow along and you'll learn everything you need to answer the questions, win the awesome prizes, and obviously the bragging rights for the entire evening. So yeah, something to look forward to. And I guess once everyone's scanned, which is also easier from the front rows, it's time to introduce ourselves a little bit more. So hello, my name is Eva. I'm a software engineer, and my journey to software development was not particularly linear. I did a bit of a career change just a couple of years ago. And the one thing that really helped me learn, especially at the beginning, was, well, for one, having a great teacher, but also to have a look behind the scenes at what's going on there. And that's exactly what I'll be doing with you today. So I'll be the one always looking under the hood to show you how the compiler actually thinks. What is it looking for? What patterns does it recognize? And how can you teach it new tricks? So whether you're new to C# or have been around for a while, I hope this talk helps you see the language in a new way and gives you the confidence to dig deeper.
And I will be Eva's coding assistant who will be implementing the patterns that you unveil and trying to shift all of these ducks to your left. Hello world, I'm Stefan. I am a Microsoft MVP, a JetBrains community contributor, and a co-organizer of the .NET meetup in Vienna. Our chairman is here already, so this does not make me nervous at all. Apart from preparing talks and loving about chatting about .NET, at my daytime job I'm at Century, where I build error monitoring solutions and observability for your every application.
Awesome. And Stefan and I also have a live stream. It's called To Code or Not to Code, and it's our bi-weekly excuse to code together. Well, sometimes we code, sometimes we just debug for hours or go on ridiculous tangents, but we always have fun, we always learn a thing or two, and every now and again, we build some really cool stuff. And I'm not just saying that to advertise our stream, I'm also saying it because this talk actually came out of one of our episodes where we built a source generator that lets you deconstruct any type. Now, what does that mean? Let's see. All right, okay, so we can already see we've got our talk class here. You might already spot this little attribute up there. That's from our source generator. And then we've got three accessible properties. I'm not going to scroll down, but this is title, meetup, and start. And up here we create a new instance, and this is obviously where it gets interesting. So this is the deconstruction syntax. On the left-hand side, we declare a tuple of variables. On the right-hand side, we've got the instance of our class, and once the deconstruction is complete, you can actually use these variables just like any other local variable, and for example, print it to the console. And now this all compiles because of our source generator. You can, it's already a little teaser, if I remove this attribute, we get, so the last row might not spot it, but there's a little compiler error here. So that tells me, yes, indeed, I need this attribute. And when I run this code, hopefully the deconstruction is successful, and it is, and we can print them to the console. Awesome. Now, as promised, let's have a look what makes this tick. So what's happening underneath the hood. I'm going to open my IL view. I'm going to go to low-level C#. And here I can already see that we call deconstruct on our talk class, instance of the talk class. And this is actually what was missing beforehand when we had the compiler error, because as soon as the compiler sees the deconstruction syntax, it is looking for a method called deconstruct, exactly deconstruct, can't have any other name, and it's also checking that it has the correct out parameters here as well. Little fun fact, a record class that can do this out of the box, and as chance would have it, we do actually have a record here. Yeah, I'm just gonna run this real quick to show you it prints well as well, perfect. And if I have a look under the hood, well, I have to scroll a little bit to the side, and here we can see it calls this exact method again. So the compiler doesn't care whether the deconstruct method is emitted by a source generator, whether you're using a record class that does it out of the box, or whether you add it manually yourself, because it's a pattern, and it's our very first pattern of the day. So let's say you don't want to use a record. You want to use just a regular class. And let's also say you don't want to use the source generator that some shady people wrote on a live stream. And now we have, again, this compiler error. And if I hover it, it already gives you the hint, no deconstruct method with 3 out parameters found on the type talk. So Stefan, can you, for the first duck, manually add this deconstruct method? Because if you do it just right, the compiler should think if it looks like a duck, swings like a duck, and quacks like a duck, it probably is a little deconstruction duck.
Let's deconstruct our first pattern. Now, usually with patterns, they need to be accessible from the call side. For the sake of this evening, we will keep everything public. But since we are in the same assembly, we could also make all of the patterns that we show tonight also internal, because, well, we are in the same assembly. If we would be crossing the assembly boundary, they would need to be public so that they're accessible at call side. Now I'm going to declare this as an instance method. Our source generator declared this as an extension method. And not all patterns, but most patterns that we show tonight will work as either an instance or an extension method. So now let's provide this instance method. It is void returning and is called exactly deconstruct. Now we don't need, it can't be empty. We saw it needs to have 3 out parameters. So I'm actually gonna copy the signature of the constructor here, and we'll be adding an out before the 3 of them. And when I added the last out, we see that the compiler error up here already disappeared. So the call side is now satisfied, the pattern is fulfilled, and the compiler is already binding to the now available deconstruct method. But our implementation, well, doesn't just work yet, because when we have out parameters, they need to be definitely assigned within the method. So let's do exactly that. We assign the title to the title property that we have. We will do the same for the meetup string and also for the start. And now when we run this, we should observe the very same behavior that we did with the source generated deconstruct method, or with the one provided from the record already. Deconstruct methods are overloadable, not by type, so I couldn't provide another deconstruct method that varies, for example, in one type, but I can provide another method that varies by amounts of arguments. So for example, I want to have a deconstruct with 3, but also a deconstruct of 2, which just carries the title of our talk and the name of this meetup, the .NET Stammtisch. So if we were to remove the third variable, the date time. Now we get another compiler error saying that this time the compiler is looking for a deconstruct method with 2 out parameters. Let's provide exactly that. I will duplicate this method, get rid of the third one, and by the time we have done that, again, compilation is happy. It binds to the now with 2 methods deconstruct, and when we run it, we deconstruct into local variables the title and the meetup.
Awesome. That's the first duck down. All right, and the first pattern down, but we're still in the warm-up phase, so we're gonna start with another very, very simple pattern. I'm just gonna have a list of int. I'm gonna initialize it like this, and let's just do that. Awesome. Let's also foreach it, just so we have something to look at. I don't know, item in list, and then yes, let's print it to the console. So, item. Okay, perfect. All right, let's do a quick sanity check that this indeed works. You never know, live coding. Okay, woohoo, we can print all of the items to the console. And so this next pattern is actually about this collection initialization here. So I want to have a look underneath the hood and see how this works there. And you can see we create a list, and then we call add once for each item in the initializer. And that is actually our very next pattern. So let me close this. I'm just going to duplicate this, because if I have my own list type, our list, I'm also going to call this our list. And let's also switch things up so we have slightly different output. Our list doesn't exist, so let's create it. But it doesn't compile because it doesn't match the shape the compiler is looking for. We just saw the shape, and again, we get a little hint when we hover here, cannot resolve symbol add. So Stefan, for the next duck, can you manually add this behavior to our list and make our list quack like a proper collection initializer?
Not only am I going to add the add method to our collection, but also hopefully another duck to my collection. If I move the mouse just a little bit to the left, we see there is actually another compiler error. For collection initializations to work, we also need to implement the IEnumerable interface, because the generic type of the enumerable interface is then declaring the type that is expected for a collection initialization. We learned this the hard way. So let's first provide the IEnumerable interface. It's also generic since our list is generic. What I'm now thinking about, I want to make this type sealed because I get a little OCD if public types are not sealed. And now let's provide the add method. So we have public. It can be void or returning. For this, the compiler will ignore the return value. It could also return something, but for our sake, it will be just add. It will be void. We call it add. Since we have a generic collection, we will have a generic parameter. Let's call it item. And we already see up here, we don't have any compiler errors anymore. The compiler is now binding to this add method and calling it 5 times in our case. Now, we still need an implementation to actually run that, so let's do just that. For most of our demos for this evening, we will use an existing type from the base class library to make the implementation rather simple. But yeah, the compiler for patterns doesn't see private implementation details. It only looks for the public API shape, or the accessible API shape, because this one could be internal as well. So let our list be backed by a good old generic list. And for the, let's just forward to the existing add. We also need to implement the IEnumerable interface. Let's do just that and forward to the getEnumerator method. So we have a bit of a delegating implementation here. And yeah, we fulfill the pattern by having the IEnumerable implemented and having the add method that the compiler is now happily calling. And we run this, we should now get, well, still 0 to 4, but we can now switch to our list and should get 5 through 9. And there we have it.
There we have it. And well, we can also initialize dictionaries, right? And since dictionaries are kind of like a collection of key and value pairs, I was wondering if we could also overload our add method to take 2 values.
Let's give it a try. For a bit of more visibility, I will put a couple of new lines in here, so different syntax, but same semantics. What you can always do, also with a regular list, you could add braces for each item as well. We see that Ryder is highlighting these having a little bit gray shade, so they are redundant here if we only add a single, if we only call add with a single parameter. But if you want to call it with two arguments, for example, with a dictionary where we have a key and a value, now we need those braces. And we see another compiler error where the compiler is now, well, it recognizes there is an add with one parameter available, but we actually invoke it with two arguments. So let's provide just that add method. I will duplicate this method and we'll add another t in here. Let's call it item 2. And again, the shape is now satisfied and this compiles now. And if you were to look in the source code of dictionary, well, if you would look at the source code of list, you will see an add method that takes a t. And if you look at the source code of a dictionary, you will see an add method that takes a t key and a t value.
So, I guess that's your next doc, isn't it?
Yes, it is.
And I can also see that the IDE is also screaming at me to, of course, not initialize it like this, but instead, to use the collection expression. And I'm very happy to do that because, first of all, it looks a lot cooler. But let me just build this so we can have the updated version underneath as well. So if I go to my trusty low-level C#, I can see that well, they both look the same on the left-hand side, right? We saw that both our list was also doing the collection expression. It looked like it was doing the same thing, but underneath the hood, it is actually not, because for the list, we now have a stack allocated span that is being used to fill the list in one go, which is obviously super, super cool. But our list, Stefan, is still using add, which is obviously not great because it could potentially grow the underlying array of the underlying list. So first we get an array of 4, but then when we add the 5th element, we get an array of 8. We have to copy those values over. It's just not ideal. So Stefan, can you please also enable this span-powered collection expression magic? Here's your duck.
I see span. I love span, sometimes a little bit too much.
It's true.
What I'm going to show now, we will not see on list because the compiler knows the type list intrinsically. It has been there since generic, and for the core types of the BCL, the compiler has intrinsic knowledge. So it knows how to most efficiently initialize a list. In earlier versions of the compiler, it didn't know how to most efficiently create an immutable array. By now it does, so what I'm going to show you is still there for backwards compatibility. But when this feature was first introduced, in order to make an immutable array collection initializable, the team added this collection builder attribute, which is teaching the compiler on how to most efficiently one-shot initialize a collection, not by calling add x times, but calling, in this case, a method create that is on the type immutable array one single time to get a one-shot initialization of that collection. And with that attribute, we're now going to educate the compiler on how to one-shot initialize our very own collection. So I'm going to copy this attribute, switch back to our source, add this attribute to our list. And of course, well, we cannot create an immutable array here. We want to create our list. So the first argument is the type where this method will be found on. But this must be a non-generic type. So we can't put this static create method on our list. The pattern usually is then you have a non-generic class that holds this factory methods. So we'll create an our list type. And the second argument will be the name of the method which should exist on this type, which is usually create. But that's just a convention. You could call it whatever. And to be refactoring safe and we can navigate in our IDE by clicking F12 or hitting F12, let's use the name of operator and call this ourList.create. Now let's add this type and this method. So again, it needs to be accessible. Let's create a static class ourList, non-generic. And let's add the create method. Public, it needs to be static because it's a factory method, create. Now the return type can't be void because we want to create something. We want to create our list, a generic version, an instance of our generic list. That means the create method also needs to be generic. Now for the parameter, we see that the compiler is creating a read or a span, which is using it as a buffer in order to one-shot initialize the collection we want to create. So we need to pass here, we need to accept a read-only span. And the span is essentially a view into contiguous memory. This could be backed by an array, could also be stack allocated, or even some native memory. Now we see in our little scroll bar here, there is no red anymore. If we scroll up, so the pattern here is already satisfied, but as always, let's also get the implementation detail right. So let's return a new instance of our list, passing in the span, and I'll be creating a constructor here. Which is now accepting the read-only span. And as an implementation detail, let's add to our list that our collection is backed by. And if we run this, now we should have indeed a one-shot initialization of our list, and we should still get 5 through 9. But let's actually see if it does work indeed. Let's take a look at the decompiled code, and now see that indeed the ourList.create generic method is called. If we take a further look in the implementation detail, we see some one-time helpers and stuff going on. So what the compiler is actually doing, it's kind of baking in this collection somewhere into the assembly and then pointing to that with that span. So this is indeed the most efficient way of how to one-shot initialize our list. And if I didn't forget anything, I've earned myself another duck.
You did. However, it does sort of remind me a little bit of an episode with Stuart Lang that we had on our stream, Slide Product Placement, where we explored everything about collection expressions. If you're interested in rewatching it, all of our episodes are on our YouTube channel. All right, so now for the next pattern, I want to access the individual members. So I'm gonna have, yes. Yeah, I'm gonna access the first item of our list. I'm just gonna go in with an index of 0. That should be working perfect. And then for the last item, I'm going to use the from end syntax. So I'm gonna do _1, which should be the last item, _2 would be the second to last item, and so on and so forth. And what's interesting about this is if I hover this, you'll see that it's of type index, which is interesting because list does actually not have an index-based indexer. It has an int-based indexer. But it does compile, and actually when I run it, we'll hopefully get, yes, we will. Well, we get the right output. We get the first and the last item of our list. So how does this work? Well, let's have a look. Yeah. Okay, so I can see already, well, maybe have you spotted it already? Well, here we are. So this from end syntax under the hood is calling list.count -1. So _2 would be -2 and so on and so forth. And actually with the count and -1, we actually get the int-based indexing that we were looking for before. And this is how this works underneath the hood. And I guess you kind of get the hang of our talk now. Obviously, what I really want today, Stefan, is that our list can do the same thing. So for the next duck, could you please, here's your indexing duck. Go crazy.
Am I only allowed to use the index finger?
Yes.
That's gonna.
Is that the index finger?
Oh no, that's the pinky.
Yeah.
That's the index, right? Okay, that was embarrassing and it's on camera. Okay. But if this should be the only fail, then I guess I'm happy. All right, let's provide indexing. How an indexer looks like, again, we need to make it accessible. It returns usually the element that we would also return by the enumerator. The keyword is this, and then we have those brackets where we could pass in now an index. If I was using the system.index type directly, we see compilation is already working and it would bind to this indexer, but this is explicit indexing. We're really using the index type. We want to get the C# pattern in place, which is the implicit indexing, so we only provide an int-based indexer. But yeah, the from-end semantics does not work yet, because we need to educate the compiler of how to start from the other side, which is we need the count. So let's provide another property, which is usually an int called count, and at the call side, compilation is already satisfied, the pattern is fulfilled. Now let's just get the implementation detail right by forwarding to our list with that index, and with the count we return the current count of our list. And we run this, and we now should get the first and the last element, being 5 and 9 from our collection. The compiler doesn't only look for count, it also looks for length. If we were to provide a length property, we see the count is now a little bit grayed out. So if we have both, the compiler is preferring length over count. There is a bit of a semantic difference to using length and count. When you have a fixed size collection, like an array or a span, this is usually a count. So this doesn't, no, a length, excuse me. You have a length. It doesn't grow or shrink in size during its lifetime. With lists or dictionaries, you can add and remove items. So they may grow and shrink over time, and then you use a count. So you can take a look at the BCL if they implemented this pattern on all of the collections correctly. You theoretically could provide both, but semantically it doesn't make any sense if you have a collection that is both fixed size, but can also grow and shrink in size. So use the one that's the observable truth to your collection, if it can change in size. Now let's also check if we're not using caret 1, which is the last element. If we use caret 0, which is actually the count or the length, we would now index into the length. But the indexes are 0-based, so we'd be actually overshooting by 1, and we should run into a good old argument out of range exception, and there it is. So our indexer works as expected.
Awesome. Really cool. All right, let's slice things up a little bit. I'm going to get rid of some noise here, and I now want to use range types. So I'm going to do 2, 3. Yeah, so if I hover this, hopefully, yes, it is of type range. And so range has an inclusive start and an exclusive end. So we want to start at 1 inclusively and end at 3 exclusively. So we should actually get 1 and 2 printed to the console if I run this. And we do indeed. Awesome. But yeah, okay. Actually, let's have a look what this looks like first. Let's go step by step, shan't we? All right. Underneath the hood, what we call, well, I already kind of gave it away, we call slice. So we have another wonderful method that is another pattern, and it's called slice, exactly slice, and it has 2 arguments. It has a start and a length. So we start at 1 and we go 1, 2, and then we have the view into our collection. But we've just had the beautiful from-end syntax, and so if caret 1 was the last item, caret 2 should be the second to last item, and we're still in range, so this is still exclusively, so I am expecting the exact same behavior, and I get the exact same behavior, and let's have a look what this looks like in here. Well, we still have the slice method, and the start is still the same. Oops, arrow here. But obviously the length is now calculated differently. Well, the first part is, again, just as we had before, count -2 because that's after the caret, before we had -1. And then we again have -1 because we obviously don't want to start at the beginning. We want to start at index 1. So we need to get rid of that as well. And this is how we get to our range. Well, Stefan, can you slice up our list as well?
Not only have we enjoyed already previously some slices of cake, now we're going to enjoy some slices of our list. Well, since this is a range type under the hood, we could again be explicit about it, create another indexer, make this range-based, and return an instance of our list, and we would already work as expected, but, well, there's a little bit of cheating because this is explicit. We want to get the implicit syntax in. And implicitly, well, we already have the int-based indexer. We have the count or the length. It's actually, this is our list. Well, we have an add method, so we can grow. So we have a count, not a length. And the only component missing now is the slice method. So let's provide a method called slice. Now, since a slice, what a slice is doing is it's providing a sub-view into the current collection. With our code here, we would be cutting off, indeed, these elements and then create a sub-view into this collection. So we need to return a new instance of our type. And the arguments that Eva showed were both the start and the length. And the compiler is already satisfied, the pattern fulfilled, and binds now to our slice method and calculating the length via the count. Let's get implementation details running as well, so we can actually take a look at when we run it. So let's return indeed a new instance of our list. And, our implementation detail, we will slice into the existing list. So a list is, that is exactly the same implementation. We need to provide the respective constructor. And if I'm not making any copy-paste mistakes, we should be able to run this and observe the same behavior. Cannot resolve. Now we have, we have list. Doing something wrong, but I can't think of it. Can we finish this one? Yes.
Parameter of the slice method is int. Shouldn't it be t? By intent.
Thank you very much. No, here was my mistake. Very good. Well observed.
Bonus points.
Yeah. Returning int. But our collection is a generic. Yes, I was focusing on the int parameters way too much. Indeed, thank you so much. This is helping us a lot. So we don't create an int, but actually the t, and now this works with the underlying list. Yeah, thank you. So now with the slice method implemented, not only the shape of it, but also with a correct implementation, we should now be able to run this and get now a slice into our custom list with element 6. And 7.
Awesome. All right, so I guess we're warmed up with our
I need to share the duck with the audience.
You need to share the duck now. So we've warmed up with our patterns, so we can go a little bit deeper, because the next pattern is actually one of my favorites. I think it's the first one that I ever learned, and it's the foreach pattern. And well, you can say, well, we've already been foreaching list and our list the entire talk, so we know it definitely works. But it's obviously because we have the IEnumerable interface here. The pattern actually doesn't need this interface. LINQ heavily relies on it, but the pattern doesn't. So I can actually just remove it. And then something down here doesn't compile. I'm just going to get rid of that as well. And, well, it compiles. Well, this is list. Let's see with our list. Okay, this compiles as well. And if I run it, we can still foreach it. So that tells me that there is indeed a pattern, and we're already fulfilling it. I'm going to have a look through your code and see what that might be. And well, just going from naming, I mean, this looks pretty suspicious. So this is what I'm going to look out for when I go into my IL view. But I'm also going to go back to list just because you can see it a little bit better there. But I promise I'll show you with our list as well what's going on a little bit later. Right, let's have a look. All right, and I can already spot this method that we saw at the very end of our type. It was the getEnumerator method here, and indeed it gets called, and it returns an enumerator. And on this enumerator, we can find a bool returning move next. And while move next is true, we can actually access the current property there. And then also right at the end, we call dispose on this enumerator. And that is the pattern. So in order to foreach any type, you need to have an accessible parameterless getEnumerator method that returns a type that has a bool returning move next and a current property with at least a get accessor. The dispose is optional, but it is definitely best practice to have it. And yeah, well, we saw before we have this method and it returns an IEnumerator, and that must fulfill the pattern some way. So now the challenge is, can we write our own enumerator? And here is our enumerator duck.
Let's enumerate through the for each. Well, if we take a look at the enumerator of list, well, we will see list actually does implement its very own enumerator type. This is a struct, so that when we for each, we don't have any additional heap allocations. And taking a look at the IEnumerable interface, we see there is also the getEnumerator method, which is now returning an IEnumerator. And this very IEnumerator has the current method, the move next method, that's on the non-generic one. And now we're gonna implement our very own implementer, but we don't need those interfaces necessarily. As we saw in the list, usually when you have a custom enumerator for a very specific type, it's usually designed as a nested type in this collection. So let's jump, we are in our list, and let's just create a nested type in here. Now I'm gonna use a ref struct here because I wanna use a span under the hood as an implementation detail, and only ref structs can contain ref fields like a span is. So let's declare a ref struct. Ref structs must always be on the heap, they cannot be boxed, must always be on the stack, they cannot be boxed onto the heap, and call this our enumerator. This does not need to be generic because we are already in our generic list, so we already have the generic T as a context. And let's return a new instance of our enumerator. We pass in the list that we later on use for the implementation detail. And now provide those two necessary methods or members. We provide the bool returning move next method that is parameterless. And we provide the item returning current property. Since we are generic, we return a T here. And when we scroll up to the call side, we see we are already foreachable by using our very own enumerator instance without having the IEnumerable interface implemented. What we see as a side effect is for collection initializers, the collection must implement IEnumerable. For collection expressions, the collection doesn't need to implement IEnumerable, but it still needs to have this IEnumerator method that then returns a T in the current, otherwise collection initializers don't work, and we run into this. We learned it the hard way.
We learned it the hard way.
Now, with the compiler satisfied at call site, let's also get the implementation details working.
You're still using the wrong list at the call site, the list and not our list.
Indeed, indeed. Let's see if it still works. Yes, it does. Thank you very much. And yeah, now let's get the implementation details right. Enumerators, we have a move next that is called multiple times, so we have some state machine going on. We're gonna represent the state machine or the state with an index. We start at -1, which in our case means the iteration hasn't started yet. And I mentioned I want to use as a backing memory store, I want to use a span. So let's create a span of T here. And I'll do now a little bit of unsafe code. I can go with the collections marshal. I can get the actual memory that is backed by our list as a span. And now we just implement these two methods. So for the move next, we move our state machine forward. So we're gonna increment our index. And we must return true if there is still another item. So if we haven't completed iteration just yet. When we return false, that means we have now iterated through all the items, and iteration should stop, which is then the signal to break out of the while loop. So as long as our incremented index is less than the span's length, we return true. And for the current property, it needs to be at least a getter, we just index into the span. And now also with the implementation detail right, we should be able to iterate through our list and getting 5 through 9 without implementing the IEnumerable interface and using a stack allocated enumerator, so we are iterating this as efficiently as possible. Another phenomenon I want to show is that the return type of the current is critical for the variable that is used during iteration. So if we wanted to, for example, have a ref int here, we need to update our current property and return this by ref. And yeah, depending on this t here, the return type of current will dictate the type that we use in the foreach.
Cool. Well, not too fast. Let me check if this is all correct. Oops. Let me tap into the foreach. Okay, well, for the pattern. So I'm checking the pattern. And I can see if I scroll all the way to the side. Okay, we call the getEnumerator method here. That's wonderful. Let's go back. All right, I see move next. I do see current. Wow, my arrows are on point. What I don't see, however, is the dispose. We're still missing that. As we've just proven, it is not necessary for the pattern, but it is best practice to have it. So I would say let's add that as well before you take your duck.
And this is one that I need to earn.
Yeah.
The audience is gonna help me, I'm sure. I lost my trail of thought.
Help.
I totally lost my trail of thought.
We need dispose.
Dispose, yes, thank you. So let's make our enumerator disposable. Let's implement the IDisposable interface. Let's add the dispose method and as evidence that it's actually called, let's print disposed. So we should now get 5 through 9 with a disposed at the end. And here we go.
Okay, but we are working with ref structs, right?
Yes.
And they were only able to implement interfaces since, I don't know, C#, what is it, 13?
13.
Okay. So what if we were working with the previous version? What would we do then?
So let's trail back to the past. We're targeting .NET 10, and with that we get C#14 as a language version, but we can, we can disjoin the target framework from the language that is used by the compiler. So let's downgrade to lang version C#12. And with C#12, ref struct, there we go. Ref structs are not able to implement interfaces, and the compiler, modern compiler then says, ref struct interface is not available, please use C#13 or higher. So, all right, so I need to remove this interface, but how can I now get the dispose in for our enumerator?
I mean, it still compiles.
It does.
Maybe it still works.
Let's give it a try. Ooh, we still get the disposed even without the interface.
That seems like a pattern to me.
Ooh, let's find out if it really is. Let's declare our own, our disposable. Let's create the type. Our disposable. If we implement the interface IDisposable and implement the method, we see this works. If we were to remove the interface, okay, so it doesn't work for regular classes. What about structs? If we change this to a struct, for structs, we still need to implement the IDisposable in order to make the using declaration work. So only for ref structs, because at the time ref structs were introduced, I think C#7 point, some point release, we didn't have C#13 yet, so we couldn't implement interfaces on ref structs. So for ref structs, disposable is a pattern, but not for classes nor regular structs.
All right.
Did I earn this? Did I earn this duck now?
You did earn this
Yes.
duck. Good job. All right, I think we're ready for some async magic now. So I'm going to await my for each, and I'm going to have here a method called get items async. Async. Yes. And OK, for a second I thought it would compile. All right, let's declare a static async. Async. This is why Stefan is typing more than me, because I'm so slow. Async enumerable. But it's not, the autocompletion is also not. Of int returning method get items async. Oh my goodness. All right, and in here I'm just going to have 4 with an up of 5. I'm going to await just a quick task.delay of 500 milliseconds. And then I'm going to yield return I. All right, this was scary. Awesome. Did I have a typo? Yes, I did. Woohoo! And the ref is still there. I'm just going to get rid of that, if that's OK with you. Perfect. All right, if I run this now, I should get the items printed, but with half a second delay. So that's wonderful. So a nice example for our next pattern. So I'm going to have a look under the, OK. Well, we're in the async state machine now. So this can look a little bit scary. It definitely did for me the first time I saw it. But we can spot some familiar faces. For example, I can see get async enumerator. So we just had get enumerator, now it's get async enumerator. So that's pretty cool. Down here, or up here now, I can also see move next async. So we had move next, now it's move next async. And down here we can also have the current property, which is obviously a property and therefore synchronous, oh, not async. And these shapes, so this get async enumerator up here, the move next async, they are not accidental. These are the async equivalents of the for each pattern. And yeah, well, with this pattern, you can async for each any type. For example, our list as well. So here's an async enumerator duck for you. Enjoy.
So the async state machine, that's still haunting me. My very first talk that I gave 6 years ago was about async and await. So yeah, it will always chase me. All right, so what we saw, we essentially now need to provide an asynchronous enumerator, not a synchronous one. I don't want to obliterate any of the behavior that we already added. So I'm just going to copy our existing enumerator type. And we'll copy the get enumerator method to instead be called get async enumerator, which should now return not our synchronous enumerator, but our async enumerator. Got shifting some types around. Now, when we talk about asynchrony, there might be threads involved. And each thread has its own stack. So we can't use ref structs anymore because they're always stack allocated. So we need to transfer some data. The data flows in the asynchronous state machine. So in this case, we need to use a good old class now. We could also use a struct because the structs are allowed to be boxed onto the heap. So we can't use span anymore. We fall back to just a good old array. And we'll just to array this list here as the backing implementation detail. And yeah, well, we still got problem here at async enumeration. So let's get the pattern of our async enumerator right. Instead of move next, we will have move next async. And instead of returning a bool, it must return something awaitable that returns a bool, like a task or a value task. So let's return a value task of bool, which means we can now make this method asynchronous as well. We can add the async keyword, give this implementation a body instead, and also have the same await that you have in your code. Let's do await.task.delay of 500 milliseconds. Now, current is just a property. It cannot be asynchronous, and we saw that it's already using that as well. So with any luck, or without too much bad luck, we should now have asynchronous iterations with our list with the same behavior for waiting 500 milliseconds from 5 through 9.
Pretty cool. Well, we had dispose with the synchronous pattern. Do we now have dispose async?
Yes, we do.
Okay.
So let's jump to our async enumerator. Let's implement the async disposable interface, which now doesn't have dispose, but dispose async. And avoid returns into a value task. And we could now await here as well. Task.delay. Maybe let's make this 1000 milliseconds, so
goodness.
an entire second. This needs to be async. And now running this should print the items as we had before, but then waiting another second and then say this post.
All right, bets are on. Dum, 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 dum.
I shouldn't have added a second.
You shouldn't have added the whole second. Awesome, but do we actually need this interface? Because, I don't know, could be a pattern hiding there.
Let's give it a try. Remove the async disposable interface, just keeping the dispose async method as a pattern. And let's observe if we see the same behavior.
Bets are on.
Right.
Ta-da!
There we go.
All right.
So disposal or async disposal also seems to be a pattern. Let's dive a little bit deeper into it and let's see if that's also a pattern for other types as well. So let's create our async disposable. Public class our async disposable, which implements the async disposable interface. We will generate the method. Yeah, implementation doesn't matter. Let's see. So and now let's remove the interface. So we see for async disposal, since async disposal was added later, dispose is a pattern also for all kind of types. So not only for ref structs as with the synchronous version, but also for regular classes, regular structs, compiles as well, and ref structs as with the other one.
Awesome. Very versatile. Well, I'm slowly running out of ducks, but I've still got one left. So one more. This is super satisfying. I love just deleting everything. Just clean slate. All right.
Aww.
Oh my goodness. Right, line. I'm just going to have another really quick example before. And I'll just have a date. Oh, that's annoying. Time off. Set. Yes. Now. All right, perfect. So this worked. Awesome. And I'm going to have after as well. After. And then in between, I'll just await task.delay. And I'll have a time span from seconds. Let's say 2. All right, that looks pretty good. All right, let's have a quick sanity check. Live coding is hard for me, apparently, but not for you.
It's always hard.
It's always hard, okay.
It gets easier.
Oh my goodness.
But never easy.
What did I do?
No,
Oh, okay. It's just built for so long. But okay, we get the right output. So get the date time with 2 seconds delay. I just wanted to have a quick await example here. Well, let's go underneath the hood. We've got a clean slate, but actually, when you go into the async state machine, still, I sometimes get so, I don't know, confused. Some of you might be, can I zoom out a little bit? Well, maybe like this. Sorry, last row. you can come to the front for this final example. But yeah, just so we can see kind of, so how I sort of start with this is like I look at what can I see from the code. We've got 3 lines of code. Let's just spot what we can spot. We can spot the before, we can spot the after. Everything else needs to happen. In between, I can also see the task delay. And then I can see that we call get a waiter. And this is another pattern. And this method returns an awaiter. And this awaiter is completed. And if the awaiter is not completed, then we go in here and we record the state. And we can also see that we have the async method builder here. We call await unsafe uncompleted. And we pass the awaiter in here as a ref. And that tells us that we need to implement one of 2 interfaces, the INotify completion interface or the ICritical notify completion interface. And then once the awaiter is completed, we actually call get result down here. And that's the pattern, super easy. And there's so much red on the screen, but I just really quickly, what I want to draw your attention to is the get awaiter method that returns an awaiter. We have the is completed here. We have the fact that the awaiter is passed as a ref down there, and then the get result. And now it's only 4, so I don't think I can make it any smaller than that. This is our awaitable pattern. And with that, you can actually make any type awaitable. For example, we could just await time span. Or can we? This duck says we can.
Let's explore. Now we need to add our own get awaiter to time span. We don't own time span. Time span is declared in the core library of the BCL. We don't have access to it now. So for this pattern, we're now going to use an extension method. The compiler doesn't work for all the patterns we show, but for most, with extension methods as well. If you have, for patterns that support both instance and extension methods, if you have both, the compiler prefers the instance method over the extension method, just with regular overload resolution and binding. All right, so let's create our own extension method. So let's do public, static, class, our extensions. We could use C#3 style extension methods, but we want to be modern, and we're going to use the C#14 style extension members. If I would start to write the extension keyword here, we should get a compiler error already saying that, oh yeah, well, it doesn't say that, but we are still in the past. We switched back to C#12, where this feature didn't exist yet. So let's go back to the future, or let's remove this altogether, because the default language version of .NET 10 is C#14, where we have extension members now available. So we will extend the time span. I need to provide the method get awaiter. It's parameterless, and since it's a get method, it needs to return an awaiter. Let's return a task awaiter, which is an awaiter. And we see it's already compiling at the call site, so we now call the get awaiter and can create this async state machine. Let's get implementation details working as well. And let's return the awaiter of a task.delay. Writing your own awaiter is quite tough, so I'm going to resort to the existing functionality from the BCL, and we'll get this awaiter. And now if we run this, we made time span awaitable. And yeah, we could even make an int awaitable, but at some point syntax gets crazy.
Yeah, but isn't this cheating, because we're still using the built-in task awaiter? So I want my own awaiter, please.
All right,
for the duck.
For the duck. So can we build our very own awaiter? Well, yes. So let's provide our awaiter class, which now should have those 3 components that you showed. First one is the isCompleted property, which the compiler or the runtime is checking at the time of the await. Is the operation completed already? Because if it is, there is no asynchrony going on. Code will just continue to flow. If it hasn't completed, then the state machine will kick in, record the state, and at some point will return back to this method. You mentioned interfaces, so we can implement the notify completion interface or the critical notify completion interface. The critical notify completion interface is also implementing the interface. So we have either the onCompleted method or the unsafe onCompleted method. Depending on what the state machine chooses, one variant is flowing the execution context, I think, and the other one is not. So let's implement the missing members. And for the last component, we need the getResult method. In our case, it's void. So what would getResult do if it returns void? It would rethrow exceptions that have happened or may have happened during the asynchronous operation, so that at the time of the await, if stuff goes wrong, the exception bubbles back up. And we could catch it or not, let the process crash. We see even without returning an existing awaiter. Now we return our own custom awaiter, and compilation is already satisfied, so the pattern is complete. Let's also get implementation details working. Again, writing your own awaiter is quite tough, so I'm gonna again resort to existing task awaiter as an implementation detail. Task awaiter, where we say task, dot delay with the time span that we pass in, get awaiter, and now I will just forward to the implementation that the BCL is providing is completed, uncompleted, on unsafe completed, and the get result. The action here, that's the continuation. So at the time of the await, if at the time of the await, the awaiter is not completed yet, everything that is after the await is a so-called continuation, which will be represented by this action that then we call back into, or the state machine calls back into. So I think we just need to actually now return our awaiter here. And this should fix all of the implementation issues. And now with the pattern manually satisfied, we can have our own awaiter, and we now super customly await 2 seconds, or a time span of 2 seconds.
Yeah, but your get result is still void. Yes, so don't take that duck yet. Because I was wondering, can we also return something? Like, for example, time span, like delay, like return it like this. Maybe also print it to the console. Delay. Like this. What do you think?
Yes.
Yes.
It's almost as if this is scripted. All right.
What?
So now, similar as with the current of the async of the for each, where the current property, the return type t, dictates the variable that we use in the for each. The return type of get result dictates the result of an await operation. So if the get result is void, await does not return anything. If get result is non-void, well, it returns its return type. So instead of returning void, let's return the time span here. So after we got the result, now also get the implementation detail right. Let's indeed return this time span that we recorded. And we should now observe the very same behavior, but now we have an operation that returns something.
Amazing. Well done. You earned this duck as well. And now please make sure to press submit on all of your quizzes for the chance to win some awesome prizes. Just be aware that it's also time-based, so even if you get all the answers correct, somebody might have been a little bit quicker than you, but definitely, so press it quickly. And well, by now, you'll probably see patterns everywhere. And I do have a little bonus content duck here. Don't worry, it's not part of the quiz, but something more for Stefan to do. For example, you can show me the async method builder pattern.
Yeah, so now this is a pattern that you rarely encounter, but just for the sake of completion, we could decompile into the async state machine, and we see that the async task method builder is used. Currently, we use the default async task method builder, but with our own awaiter. We could also write our own task method builder that then needs to fulfill the pattern of what we saw, like having this await, unsafe, uncompleted method, and so on. We prepared this as an example already, so now I'm going to do what you earlier did, delete everything.
Woo!
It's fun.
Yeah, that's good.
So we have more patterns dot run async. We're going to await. If we jump into the implementation, it's essentially the very same that we had earlier. When we run this again, we have a 2-second time of delay. But this time, not using the default async method builder, but using our own method builder. Here, now the state machine is using our custom async task method builder. And this works by either attributing your custom awaitable or the method. This is what we chose here. So we are attributing this method with the async method builder and tell the compiler, please use this async method builder. And our async method builder, now fulfilling the patterns of having a create method, having the await unsafe uncompleted method that we saw. We can set an exception should something go wrong. We can set a result if everything goes right. And we can return a task here, which is then the result of this asynchronous operation. For example, this is how a value task is implemented. If we would take a look at value task and peek into the source code, we say it has the async method builder attribute declared. And then in this async method builder, if you dive in, this is where some reusing is going on, so that in some cases, or in most cases, the value task is maybe more efficient than the regular task.
Awesome. And another pattern that you might have spotted throughout the talk is the interpolated string handler. I think we've seen it quite a few times. Almost every time. Yeah,
every time we use the dollar quote syntax, and having some string literals and some interpolation holes that we fill with values. Under the hood, what the compiler now does, in earlier versions, I forgot which version, in earlier versions the compiler was using string.concat or string.format. But this is not as efficient as it can be. In more modern versions of the language and the library, there is now a so-called default interpolated string handler, where we now see these components being used. So for every string literal that we have in our interpolated string, we call append literal on this string handler. And for all of the interpolation holes, we call append formatted. And with that, this is indeed another pattern. So what we could do is go into our program, have even more patterns. Even, yes. Checking into the code, and well, what it does, I provided here a logger that has a log if. If it's true, it should print this message, but also it simulates a structured logging, so also the parameters that we fill in dynamically, but also the entire template for this message. And if you return false, it shouldn't do any string assembling. So it should do, if nothing should be logged because this condition is false, no operations should be taken place in order to assemble this string. So because that's the best performance optimization that you can do is not doing anything at all. So if you're not gonna need it, don't create it. And this is essentially what you can do is pass your own interpolated string handler to specific methods, which is then used when you use string interpolation. And yeah, if we jump into the implementation, we will see there is the append literal, append formatted in various forms. And the cool thing is now we can actually then in the implementation also understand, like we can return something like, is this condition that we passed in true or false? And if it is, we actually do assemble a string. And if it isn't, well, in this case, we just print whatever we got in, but not doing any work. If we run this, this must be task. We see for the log true, we get the entire thing, we get the constructed message, so the interpolated string. We can get the original template, but also the individual parameters with their indexes that we added them at. But if the condition is false, well, we don't do any of the work. And when we take a look at the decompiled code, we see this actually happening. So for the first one, where the condition is true, we actually do the work. We call append literal, append formatted, and then assemble the string. So this will allocate a new string. But when it's false, this one is never called and no additional operations. So we don't have any additional heap allocations. And for example, this is pretty much exactly how debug.assert is working under the hood. Oops. Because debug assert will throw an exception if the condition is false, and should we pass a string to it, it will only assemble the string if it actually is false. And we will see that this also uses a custom so-called assert interpolated string handler that will assemble the string if the condition is false, and will do nothing and be allocation free if the condition is true.
Awesome. But not everything is an extendable pattern like the ones that we've showed you today. So for example, the log type that was introduced in .NET 9, it looks exactly like any pattern that we've shown you today, but even if you create your own custom type and you match the shape exactly, it will still only default back to the monitor-based synchronization. Yes, exactly. So it only works for system.threading.log. Sorry. And if you like this...
Are there some upcoming patterns in the next version of C#? Maybe?
Oh yes, of course. Of course there are. Well, if you wanna spoiler it. So we've said this for a while now, but hopefully with C# 15 we will have dictionary expressions. We've been looking forward to them for a while because that will be another pattern. So yeah, that's something to look forward to.
Yeah.
And yeah, if you like this kind of content, yes, please like and subscribe, follow us. All of our social medias are hidden beneath this QR code. And obviously our bi-weekly live stream is also something that I want to mention. You can always pop in there and reach out to us, especially the ones who've helped us throughout this the talk. We always need help on our live stream as well. So yeah, we'd love to see you there as well. And I guess I'm going to have a look at the winners of today's quiz, and Stefan has a couple of minutes for some questions.
For me to really earn this duck. Yes, please.
You mentioned you can make anything readable by extension. Can you do the same for each?
We had the extension method. We showed that we can make every type readable. Does this also work for the for each? I'm not 100% certain, but I'm fairly certain that this also works for each. Well, actually, yes, because what you technically could do.
I mean, before the latest C#
Yeah.
it wasn't possible, but now.
I'm not sure since which version, but what you could technically do is you could extend range. Actually, we don't have a demo here ready, but I tried this at home. So what you could do is, let's have a range from 1 through 9. This is a range type, and we could for each this, if you provide an extension method to range. Now, system.range is, let's actually have a range here. Let's be very explicit. Let's declare a range here, and then for each this range. Well, this doesn't work because range doesn't have an instance method with get enumerator. But I tried this at home. I don't have a demo ready, but you could try this at home. Provide an extension method on range that returns an enumerator, then stores the start and the end, and then increments the index for each move next until you hit the end, then return false, and with the current, return the current item. And I think this is something you can do in Kotlin, if I'm not mistaken. Kotlin allows this kind of syntax. So yes, you could extend any type to be for eachable. Are there some other questions?
How does that team decide to implement things via interface versus via pattern? Is there a pattern?
Mm-hmm. Is there a pattern behind patterns? When does the .NET team when does the .NET team ask the Roslyn team? When does the runtime team ask the compiler team when something should be a pattern and when not? I think I asked this question, Pieter Smith, if I'm pronouncing his name correctly, and I try to remember the response, and I'm not. I think if you want to retroactively make something work, if I recall correctly, for example, list had, when it comes to indexing or the implicit indexing with the from and semantics for list already had an int-based indexer and a count. So I think that's the rationale behind it. They decided to make all the components were available on most collections that can also be indexed by index or with the from and semantics. And then I think this is mostly for making something work retroactively. Or also if, well, it doesn't work otherwise. Like with C#12, you couldn't have an interface. A ref struct couldn't implement an interface, so you couldn't make a ref struct disposable. But still, to allow it, the compiler detected this as a pattern. They didn't retro, for example, for this ref struct disposable. They didn't retrofit this to the existing class and struct, which could implement this interface already. So I think this is the rationale behind it, but I'm not 100% certain. And well, for code like the collection expressions, I guess the compiler team could have decided to make all of the collections that are everywhere aware of, but how do I teach the compiler to make my collection initializable? So they offered an opt-in to teach the compiler of how to do it, I think. There are no further questions.
We do have some winners on the quiz. So on third place, we've got Florian. Woo! On second place, we've got Philip K. Is he here? Yes.
Yes.
And on first place, we've got Jay Kamska. Yay! If you heard your name, please come to us just in a little bit of time, or right now. There you go. Yes, I want to thank XXXL so much for sponsoring our prizes and obviously for having us. Also, the .NET Stammtisch, thank you so much for having us. And obviously to you, our wonderful audience, you've been an absolute delight. It's been such a pleasure. And yeah, with that, back to you.
All right. Thank you very much. Big round of applause.